Hello and welcome. My name is Brad Mooring. I'm on the LabVIEW Real-Time RTOS group at National Instruments. And what I wanted to go ahead and do is make a couple of recordings of the demonstrations that I had for a session at NI Week 2016 in Austin, Texas. This is because I know that not everybody was necessarily able to attend National Instruments NI Week this year, and also I covered quite a bit of material in these demonstrations, so I just wanted to make sure that there was a reference for anybody who attended and didn't necessarily catch everything. I'm not going to bother going through the notes. I'm going to just focus on the actual demonstrations themselves, since that was the meat of the session that I held anyway. So I'll go ahead and provide the notes that the slides that I provided that I used for the presentation, as well as the notes that I used just personally. I'll just go ahead and upload the PDF with that information, but let's go ahead and get started with just the exercises themselves. As you recall, the first exercise was simply downloading the kernel source and building it, making no modifications whatsoever to the kernel as National Instruments shipped it. All of the notes for building a kernel are on GitHub, on NI's GitHub group under NILRT. As the kind of landing master branch indicates, you should go ahead and pick whatever branch is the OS version that you are using. Right now we don't have a 2016 or 16.0 branch, but for our purposes 2015 is close enough. We'll just use that for the time being. And there's a .txt file that describes precisely what you need to do and resources to go ahead and get you started with what's needed to go ahead and build a kernel. So some of the requirements that you need, because of some of the expectations of the kernel build system, you will need a Linux machine to do your build on. A good question that came up when I gave the presentation was whether or not you could actually build the kernel on your target itself. That's absolutely doable. You just need to follow the instructions here, and anytime that there are callouts for cross-compilation, you simply just ignore those and treat it as if it was just a direct compile. There are a lot of good resources online on how to precisely do just that. So with that in mind, let's go ahead and continue. You just need some of the tools that are required. I would use your distribution's reference, just documentation, to find out what exactly the package names are for the tools that are required for building the kernel. They vary a little bit from distribution to distribution. I already have those installed for both x86, 64, and ARM-based builds. You're going to need the Makes Washafest utility. That is required to package up the headers, which are needed if you wanted to go ahead and reversion or rebuild the National Instruments drivers. So if you need to access, for example, the FPGA from a Compact Rio target, you would need to go ahead and, after you install your new kernel and modules, you would need to go ahead and reversion the NI drivers to work with your new kernel. As I mentioned before, just your distribution's packages required for building kernel from source. And if you are building for an ARM-based target, that's all of our Zinc targets, our MyRio, the 9060 series of compact Rios, and the single board Rios, and the SOM, or System on Module. All of these are Zinc-based targets. You would need to go ahead and install the U-Boot utilities or tools package. Again, depends on what your distribution would call it, so just do a little bit of research into what that would be on your particular distribution. Now I'm going to go ahead and clone the kernel source, and I'll go ahead, since it's going to take a while, I'll just go ahead and begin the cloning process, and I'll pick back up when it's finished, okay? So we're cloning it down, and as I said, it's going to take a while, so I'll see you back when it's finished. Alright, and it's finished cloning down the Linux source from GitHub. The reason why this actually takes as long as it does, if you're unfamiliar with Git, it's a distributed source control system, which what that means is anytime that you do that initial clone, it's actually getting the entirety of the history of that particular project and making it available on the machine where you're cloning down that repository. So that's one of the benefits of Git, is that, okay, it does download quite a bit, but you're actually able to completely work offline and not connected to any particular server. You have the entirety of the history of whatever project it is that you're working on. I could spend plenty of time talking about Git all day long, but let's go ahead and get back on track here. So I'm going to the source repo that I just cloned down, and you'll note I'm literally just following these instructions. The only changes that I'm making are the fact that I don't want to use the 2015 branch. Instead, I'll be using the 2016 branch. So if I check out NILRT pub 16.0 4.1, what that's going to do is go ahead and set up the source tree to exactly mirror what was used for the 2016 NI LabVIEW Real-Time 2016 OS release for the NI Linux RT OS. So next is setting up the tools, and I've actually already went ahead and used these two downloads. I've actually set up both the ARM v7a and x86-64 tool chains for use on my laptop. That said, you don't, if you have an x86-64 based Linux distribution, you don't strictly need to use a cross-compile tool chain, since your actual tool chain would result in building targets for x86-64. One thing to keep in mind, however, is that's not tested. It could result in issues. Specifically, I am aware that the 4.1 kernel has some issues with GCC 6.1 or 6.0 onward. So that's something to be mindful of. If you do run into those sorts of issues, of course, you just use the provided cross-compile toolchain, and if in doubt, I'd heartily recommend just using the cross-compile toolchain. So I'm going to go ahead and just skip over the building it yourself. You can, of course, use other cross-compiling toolchains. If you use an ARM-based cross-compile toolchain, just be mindful that it needs to support building targets for soft FP, just to match what is on the NI Zinc, or the NI LabVIEW real-time targets that are Zinc based. So let's see here. What I'm going to go ahead and do is, since the target that I'm going to use today is going to be a Zinc based target, it's actually a MyRIA, and you can see that it is ARM v7, so it is a Zinc based target. I'll go ahead and follow the ARM v7a instructions here, and I'll go ahead and export arch is equal to ARM, and that the cross compile to where my tools actually live. If the tools are actually on your system path, you don't need to give the full path to your tool set. All you would need to do is give the triplet, the machine or architecture triplet as it's called, to the cross-compile environment variable, but you can also give it just a full path. It doesn't matter all that much. And next we'll go ahead and issue the instruction, the command make natty zinc def config. What that's going to do is actually set up the kernel configuration to exactly match what was shipped for 2016. You can make some modifications later, but as I stated, the focus of this first demonstration is just to build the kernel exactly as it is shipped in 2016. So let's see here. Next, we go ahead and simply call make. I am going to specify to use 6 jobs, the make target NI package. And this is going to take a little bit of time, and I'll come back when the kernel is finished compiling. Alright, the build is finished up, and we've went ahead and just built an ARM-based target kernel. So let's go ahead and continue just following the instructions. You'll note that it calls out what file to go ahead and what files to copy over to the target. So let's go ahead and copy those over to my controller. So let us go ahead and SSH copy your boot NI underscore. Alright. Copy that to, again, my target is called, her name is Rio. We will copy that to boot Linux underscore runmode.itb. And that's a special file format called an image tree blob or a flattened image tree, if you wanted to find out more information about that. Next, we'll go ahead and follow on with the all targets instructions. We'll go ahead and copy over the modules. We will go ahead and use tar to archive those up, create an archive, zip it, and output it to file standard out. So it'll just pipe it to standard output, but we're going to go ahead and pipe that through to an SSH connection and extract it on the other side. And we'll use all of the files under lib, pipe that through to an SSH connection to our target admin at her name is Rio. And we will go ahead, when we log in, we will run the tar command, we will extract, unzip, and be verbose about it so we can at least see what's going on. And we'll use the file standard in. And another modifier is we'll go ahead and extract the contents of the archive using the root of the file system as the base, since we are booted into run mode. What that means is it will basically extract the lib folder from the build area to the root of the file system, meaning that the contents will show up in lib modules, since that's the directory structure that results from the build process. go ahead and run that. And goes ahead, sends all of the modules over to the controller, all of the drivers that are not built into the kernel. And as a final step, we'll go ahead and copy over the header squashfs. And this is a change from the 2015 one. The name of the actual header squashfs now matches what is expected on the target. So there's some details about renaming in the 2015 notes. You can ignore that. So we'll go ahead and copy that over to the controller, to user local inst tools. And where you would use this is if, for example, you'll see, if I go ahead, this is just a serial console that's on the 96 or the MyRio 1900. It's sitting on my desk, and you can see that I have some Rio modules loaded for accessing the FPGA. When I boot the new kernel, those modules will not load. If you wanted to use the NI drivers with your new custom kernel, you will need to go ahead and follow the instructions that are, again, covered in the GitHub documentation that we've posted. So what I'm going to go ahead and do is follow those instructions right now. So first, what we're going to go ahead and do is remove this kernel version file if it exists. This is essentially a cache of the kernel version as found by the headers that are used on the target for the kernel build. So let's go ahead and remove those local inst tools kernel version. First, let's see here. If I go ahead and just output that, you see that it's 4.1.15 RT17NI 4000F1. That matches the kernel version that National Instruments shipped in 2016. This is my currently booted kernel. This is just from a fresh install from Macs with the 2016 software stack installed. So if I go ahead and remove that file, and then I go ahead and source user local inst tools versioning utils and set up versioning env. This will go ahead and mount the header squashfs, make it available for the kernel module versioning steps, as well as make some of the tools that are required for reversioning the modules available. And Linux tries to ensure that you don't run across compatibility issues by enforcing that the modules are only loaded into the kernel that they were originally keyed to. You could kind of think of it as one of the steps is they are keyed to a particular version of the kernel, and that's because there's too much flexibility in terms of what's actually enabled or available in a kernel. This offers an extra layer of assurance that you're not going to run afoul of the behaving unexpectedly. If, for example, some configuration change didn't result in any differences in terms of the actual available internal symbols within the kernel, but change the behavior of those symbols. It's unlikely, but it's just kind of an extra safety net. So let's go ahead and call the versioning call user local inst nical, which that's the kernel abstraction layer. all of the compact Rio based NI drivers sit on top of Cal. We'll call the update NI drivers, and we will go ahead and pass it. We'll spawn a subshell to go ahead and run this kernel version command, which will go ahead and get the version of the kernel as described by the kernel header squashfs that we just finished copying over from the SSH copy command up here. And if you have used NI drivers on Linux desktop machines before, I mean, you should be familiar with update NI drivers. It's just you're used to calling it directly, not needing to give it the entire path or prepending it with a versioning call prefix or giving it a particular version of the kernel. So I'll go ahead and come back when this is done, and we'll pick up from there. Alright, it's finished up versioning the NI modules for the kernel version that we just copied over, even though we have not yet booted it yet. And basically the cal script function will tell you that basically it's ready, but it's ready as soon as you boot into this particular kernel. So let's go ahead and boot that kernel. And what you'll notice is the kernel is it will be a different version of the kernel as reported by the by Max and any of the sys API functions. The OS version will have changed, and that is because the kernel version is actually what is used for determining what the OS version is. You can see right here in some of the the startup scripts, it's able to load NI Rio SRV Compact Rio, NI Rio Zinc. BDS is up there earlier too. So what that means is if we have indeed booted a different kernel, which you can determine either in one of a few ways, we can see that, yep, okay, this was built on August 4th, which is today. If we look at the kernel log, beginning of it, we can see that it's gone off the top of the kernel log. But what we can do is, if it shows the very early boot information, it will show the actual version of the kernel that is booted. But it's the kernel log is basically a circular buffer, and if you have a bunch of outputs to the kernel log, you'll lose information. But we can still see what it would have shown if we look at this proc version file, and we can see that it's indeed not the 4.0.0 what was it, F1, but instead it's this NI G01A3, and what that is actually what's called a git hash. This is just kind of extra information, but if we look at the log, the one-line version of the log, we can see that the very first commit is actually this 01A3, so on and so forth. So it prefixes it with a G. So it's indicative of what particular version of the commit ID that was used to create this kernel. Let's see here. As we showed, the init script messages show that the NI modules have loaded. Here we have further proof that the NI modules have loaded, and we are able to use the FPGA and any other NI drivers that would have been installed to the system, we would be able to use it with our custom kernel. This, however, as we said at the onset of this particular demonstration, this is the stock kernel as it has shipped from NI. At least it uses the same exact configuration. In some of the other exercises, we'll go ahead and talk through what needs to happen in order to modify the kernel, to add functionality, to remove functionality that you don't need, whether it be for performance or for security concerns. And we'll even start talking about what needs to happen in order to modify the kernel, to develop for the kernel. And that includes some debugging. So I hope you enjoyed this just quick little run through of how to take the kernel source from GitHub on the NI group, go ahead and compile it, copy it over to your target, and boot that, and make sure that all of the NI drivers that you care about are functional. So stay tuned for some additional demonstrations.